Hello, and welcome to the Chapter 4.2 Differential Equations lecture on reduction of order. So, given a homogeneous linear second-order differential equation, y double prime plus p of xy prime plus q of xy equals 0, let me stop here for a moment. This is the general form of a homogeneous linear second-order differential equation, because if there were some coefficient here by the y double prime, all we would do is divide both sides by that coefficient of y double prime to make it so that the coefficient is 1, and then it's of this form. So this is the general form of a homogeneous linear second-order differential equation. And given any such equation, and given a known solution y1, it is always possible to find another linearly independent solution y2, and thus we have a fundamental solution set, y1 and y2, two linearly independent solutions to a second-order homogeneous linear differential equation, and then the general solution is c1y1 plus c2y2. And the technique by which this is possible is reduction of order, which works by plugging in y2 equals u of x, y1 of x. So in other words, we take our known solution y1, we append to it an unknown function u, which we'll then solve for, and we plug into the original equation, u of x, y1 of x, and it will turn out that when we do so, it will always transform this second-order differential equation to a first-order one, which we can then solve using our Chapter 2 techniques. So we'll then be able to solve for u of x, and thus y2 is u of x, y1 of x, since we already knew y1 of x. So this whole thing is dependent upon that we already know one solution. But it's an important step to then getting the second solution and thus the full solution. So let's do an example, and this example will in fact illustrate the entire method. And then after this, we'll see a formulaic way of getting what we derived via this illustrative example. So given that e to the x squared satisfies this differential equation, find a general solution to this differential equation. So first, yes, you can verify that e to the x squared satisfies this differential equation, plug it in, and you'll see that it's true. And now the technique of reduction of order. So we're going to essentially hypothesize that there is another solution, y2, of the form u of x, y1 of x, and then we'll take this and plug it into this differential equation, and we'll end up getting a first-order differential equation technically in terms of u prime of x, but then we can solve for u prime of x using Chapter 2 techniques and then get u of x. So let's plug this in and see what happens. So what is y2 prime by the product rule? First, let's simplify this. Let's just write u times y1. By the product rule, this is u prime y1 plus u y1 prime. And then if we take the second derivative, the derivative of this, what is that? That is u double prime y1 plus u prime y1 prime plus u prime y1 prime plus u y1 double prime. Those guys came from that, and the product rule on this yields those. And we can add together those two middle terms, and it's that. And now substituting these in to this equation, we want it to be true, naturally. So substituting that into our equation, we have this. So that's just taking our y2, y2 prime, and y2 double prime, and plugging them into this whole thing. So y double prime, that's this as we found, minus 2x y2 prime, minus 2y, well, y2 was uy1. And now what we'll do is we'll gather all of the u terms together, and we'll also gather together the u prime terms while we're at it. And we have that. So all we've done here is we've gathered together all of the terms with a u by it. In other words, no u prime or double prime. So we have u y1 double prime there. That's a u y1 double prime. Here's a u, so that's minus 2x u y1 prime minus 2x y1 prime. We factored out the u. And then minus 2u y1 minus 2y1, factored out the u. And then we did the same thing with these two u prime terms. We factored out the u from them. Okay, this is looking pretty ugly so far, but here's where the massive simplification comes in. Look at this part. It's the left-hand side of this equation. And we know that y1 satisfies it, since That was essentially our definition. Y1 satisfies that equation. And what does it mean to satisfy an equation? Well, it means that when you plug it in, you get the right-hand side. So we got this. That was our massive simplification, since everything to the right over here satisfied this equation and was equal to 0 and went away. And I tell you that this is actually first order. It might not look like it, but notice that there's no u by itself. There's just u prime and u double prime. So we can reduce the order, that's where the word comes from, by saying that v is u prime, and thus v prime is u double prime. And then what does this become? It becomes v prime y1, since u double prime is v prime, plus v times 2y1 prime minus 2x y1 is equal to 0. And that is first order. And we can solve v using our standard techniques from first order differential equations. And then once we get v, all we do is we integrate it and we'll have u. And in fact, while we're at it, we could plug in e to the x squared now and solve. But while we're at it, let's just continue and see how much more we can reduce it before we plug in what y1 actually is. So we can solve this using integrating factors, but I'm going to show you a trick that will kind of skip a step and make this much nicer. Let's rearrange this as follows. This is v prime over v is equal to 2x minus 2y1 prime over y1. All I did there was I moved this to the other side, divided both sides by v, divided both sides by y1, and then this y1 over y1 went away. And now this left-hand side is d dx of the natural log of v. That's because implicit differentiation. If we implicitly take the derivative of the natural log of v, it's 1 over v, and then times the derivative of the inside, which is v prime. And then we can integrate both sides and thus expeditiously solve for v dx. Okay, so integral of the derivative goes away, and we have the natural log of v is this integral. And now for this part, we can do the same trick that we did over here. y1 prime over y1 is the natural log of y1 in its implicit antiderivative. And by the way, that x squared, that was integrating 2x. So in other words, y1 prime over y1, that is d dx of the natural log of y1. Since again, implicitly differentiating ln of y1, it's 1 over y1, then times the derivative of the inside, which is y1 prime. And integral of the derivative goes away, and we have this. And remember that x squared, that was just the integral of the negative of this p of x. So we're actually going to essentially derive the general formula. We're almost done. I know this is taking a while, but you can see how much and how quickly this is simplifying. We just need to take e to the power of both sides now, and we have our v, and then we just integrate that, and we'll finally have our u. So on the previous slide, we defined v as u prime to reduce the order, and then we got that the natural log of v is x squared minus 2 ln y1. And it should be noted that that x squared, if p of x was that negative 2x, then this x squared there, that was the integral of negative p of x. The integral of negative 2x, integral of 2x was x squared. Okay, now if you were cautious, you might have noted that when we integrated both sides, we did not put that plus c. Well, that plus c, it will turn out that it doesn't matter because it just becomes a scalar. So for the sake of simplicity, we'll omit it now. If you follow it through, it just gets absorbed into this arbitrary constant c2, and it doesn't matter. Okay, now we take e to the power of both sides, we use exponential laws, and what's our trick for these? This is a common trick. We almost have an e to the ln of something, just that constant there is in the way, and what we do is we pull that up there by exponential laws. Okay, so now we have that v, e to the ln v is equal to e to the x squared times y1 to the negative 2, which is e to the x squared over y1 squared. Okay, but v, that was u prime. So we have u prime is e to the x squared over y1 squared. And then integrating both sides, we have that u is equal to the integral of e to the x squared over y1 squared dx. And recall that this whole thing started with that we let y2 be u y1. So therefore, y2 is equal to y1 times this integral of e to the x squared over y1 squared. And if we wanted to make this completely general, look to the purple. I'm using color coding. That x squared there, that was the integral of negative p of x dx, the coefficient of y prime. And we can pull out the minus sign outside the integral. And we have our formula for the other linearly independent solution. Yes, this is an integral and an exponent inside of an integral. That's what it is. And that is our general formula, in fact, for another linearly independent solution, y2, given a solution y1 of a differential equation where the middle coefficient is p of x. In this case, that was negative 2 of x, and that x squared there was the integral of negative 2x dx. So what we actually just derived was in full generality. And our general solution for what another linearly independent solution y2 is to a differential equation that is standard and homogeneous and given a solution y1 of it is that y2 is y1 times the integral of e to the negative integral of p of x dx over y1 squared dx. Okay, amazing. That was some intense differential equation manipulation and reduction. And you saw where the term reduction of order comes from. It came from that we renamed our u prime to be just v, reducing the order since the equation that we wound up with had only a u double prime and a u prime. And that is what allowed us to solve that equation for u. And now that we have this, we can find our other solution. And we have our y1 as e to the x squared. So all we'll do is we'll put e to the x squared there. And then we have our other solution, and the general solution is c1y1 plus c2y2. So we found that y2 is this for this equation. That x squared there, we got that from taking the integral of negative 2x dx. Integral of that is x squared. Okay, and y2 is thus e to the x squared times the integral of e to the x squared over e to the x squared squared dx. Using exponential laws, that is e to the negative x squared dx. And good luck evaluating this integral. This integral cannot be evaluated in terms of elementary functions. The only thing we can do for this other solution is write y2 is e to the x squared times the integral from 0 to x of e to the negative t squared dt, just putting our variable x up here and letting t be a dummy variable. And if we were to change this 0, that would just change the sliding. It would get, yes, a different y2, but it would differ by a scalar multiple. So you plug in an x, this will get you an exact output. That's the reason that we're writing it as a definite integral. We want to be able to plug in an x and get an exact output for whatever our particular y2 is there. Again, to be clear, we could make this a 5 if we wanted to, and that would be a different y2, but it would still be a solution, and all we care about is a linearly independent solution. So 0 is a more natural choice, so we'll use 0. So at long last, we have our general solution. We know that y is c1y1 plus c2y2, and our general solution is c1 e to the x squared plus c2 e to the x squared times the integral from 0 to x of e to the negative t squared dt. Okay, and good luck getting this other linearly independent solution by trial and error, because as you can see, it's not something that is expressible in terms of elementary functions, but this is still a perfectly well-defined function, and that is our other linearly independent solution. That yields, therefore, the general solution. And you can see that this is not a scalar multiple of that. They're fundamentally different functions. So my point in this example was, yes, certainly to illustrate the derivation of this general formula for reduction of order and where that term reduction of order even comes from, but also to illustrate that second order differential equations can have solutions that look like this, which are not definable in terms of any elementary functions, but which are still perfectly well-defined mathematical functions, and how to get them. Okay, so what we have shown, what we have derived, is that given a solution y1 to a second order homogeneous linear differential equation, another linearly independent solution y2 is given by this. Let's apply this in a couple other circumstances. You can verify that y1 equals the square root of x satisfies this equation. Go ahead and plug it in. 4x squared times the double derivative of square root of x is negative square root of x, and then plus root x is 0. Okay, so that's a solution. Let's find a second solution, y2, and then use that to find the general solution. And over here, I wrote this general formula that we derived for what the other linearly independent solution is. So we just need to plug into this. But we need to be careful, because we first need to get it into this form. In this case, it happens to not matter, but still best to illustrate that we should do that. This is y double prime plus 0y plus 1 over 4x squared y is equal to 0, dividing both sides by that coefficient to get it into this form. So now this is our p of x, and that is our q of x. Now our other solution, y2, that is the square root of x times the integral of e to the negative integral of 0 dx all over y1 squared, that's the square root of x squared dx. That is root x times the integral of e to the negative c, integral of 0 is a constant, all over x dx. Let's call e to the negative c just c, renaming constants. We can actually call it 1. It will end up getting absorbed, but I will just illustrate what that means. Okay, so let's pull out the c. We have c root x times the integral of 1 over x dx, which is c root x natural log of x. Okay, and yes, plus another c. This will also end up getting absorbed. We only care about a solution. So for both of these, I'll just point that out now. We just want a other solution. So let these be 1 and 0 respectively. If we let the first one be 0, yes, that's a solution, but it won't be linearly independent because it would be 0. And any set containing 0 is not linearly independent. But if we let it be 1 and let that be 0, we wind up with another solution aside from the square root of x. So our other solution is root x ln x. And I want to emphasize this is something that you can always do. When you wind up with arbitrary constants in the process of finding your other solution, you can let them be whatever you want so long as you don't abolish your other solution. So we let it be these, and that made it so that we got a y2 that is not trivial in the sense of not being 0, and that's a solution that is not square root of x. So we found that y2 equals root x times the natural log of x is another solution and is linearly independent. This will always generate a linearly independent solution. Root x ln x is not a scalar multiple of root x. So the general solution to this differential equation is c1 root x plus c2 root x ln x. That's our C1y1 plus C2y2. Okay, cool. So in this case, we wound up with our other solution being actually expressible in terms of elementary functions. In this case, we did not. Either can happen. And the main thing I want to emphasize once you plug in and evaluate is that you can let your arbitrary constants along the way be whatever you want, since we just want a solution that is not y1. And then at the end, we incorporate the arbitrary constants to generate the full solution. Now recall that given a linear differential equation, L of y equals g of x, where L is a linear differential operator, i.e. the entire left-hand side, and given any particular solution yp to L of y equals g of x, and given the general solution to the associated homogeneous equation L of y equals 0, obtained by just deleting the right-hand side, then the general solution is yh plus yp. We just add together our general solution to the homogeneous linear differential equation plus our particular solution to the original non-homogeneous one. So we found in the previous example that the general solution to this differential equation is c1 root x plus c2 root x ln x. Find the general solution to the non-homogeneous equation 4x squared y double prime plus y equals x by first finding a particular solution and then using y as yh plus yp, where yh, by the way, that guy is this, because the associated homogeneous equation to this is this. We just delete that x on the right-hand side, and we get that. So all we need is a particular solution, and then we're good to go. So look at this. Can you think of any function y that satisfies this equation? Anyone at all? Well, the right-hand side is x. If we take the second derivative of x, it's 0, goes away. So if we plug in the particular solution yp equals x, this becomes 0 plus x equals x, since x double prime is 0. So we found that yp equals simply x works. Plug in x, it works. So therefore, our general solution, yh plus yp, is c1 root x plus c2 root x ln x plus x. That's our yh plus yp. Now, reduction of order can also be used to find a particular solution, provided that we know a solution y1 to the associated homogeneous equation. So in other words, dealing with a general second-order linear differential equation where the right-hand side is now g of x, we can use a reduction of order to find a particular solution to this, given a solution to the homogeneous complement. And the method of doing this, the mechanics, are very similar to our derivation of this. Go through the derivation of what we did here, and you'll wind up with a similar vast simplification and a first-order differential equation that allows you to find a particular solution. And what you'll wind up with is this. This should look familiar. This is what we got halfway through that derivation, except now the right-hand side will be g of x instead of 0. But this is still a first-order differential equation. This is after renaming, so u prime we rename to w, and then u double prime is w prime. And that's the same thing that we got halfway through the derivation, except now the right-hand side is g of x. But this is still a first-order linear differential equation that we can still solve by using integrating factors. So that is a slick way and useful way of getting solutions to non-homogeneous differential equations given a solution to the homogeneous. So in this way, from a single solution to a homogeneous second-order linear differential equation, we can get not only the general solution to it, but also a particular solution to any non-homogeneous differential equation corresponding to it. Okay, let's conclude with having you do a problem. Go ahead and try your hand at this. So here's a second-order linear homogeneous differential equation. They tell you one solution to it, go ahead and use reduction of order to find the other solution. Pause the video. Okay, so the first thing to do is to make the coefficient of y double prime is 1, because that is the form on which this formula relies. So we'll divide both sides by x squared. We'll have y double prime minus 11 over x y prime plus 36 over x squared y is 0. Okay, and now, since we have this integral inside of an integral, we should probably evaluate this part first. So negative integral of p of x, that's negative integral of negative 11 over x dx, is this part here. That is negative, negative is positive. Integral of 11 over x is 11 ln x plus c. And remember, we don't care about that plus c. We can just not write it in the same way as for integrating factors. It'll end up getting absorbed. Okay, so y2 is y1 times e to the negative integral of p of x. We found that that was 11 ln x up there, all over y1 squared dx. That's x to the 6th times this integral, x to the 6th squared dx. Okay, so we got that y2 is x to the 6th times e to the 11 ln x, all over x to the 6th squared dx. And x to the 6th squared is 12. Okay, now e to the 11 ln x, we need to use that same trick again. You can see it's a theme. It will occur a lot in reduction of order, just as it did with integrating factors. So e to the 11 ln x is the same as e to the ln x, all to the power of 11. So e to the ln x is x, so we have x to the 11 over x to the 12 dx, which becomes that. And integral of 1 over x is ln x plus c, don't care. Same reason it gets absorbed in the ultimate solution, we just need 1 anyway. So we have x to the 6th ln x is our other solution. And our general solution is thus y is c1 y1 plus c2 y2. And I just want to point out an easy way to make a frustrating mistake. That minus sign right there. I have forgotten this a couple of times, and it's very frustrating getting halfway through a problem and then realizing something is amiss. So don't forget that minus sign. All right, that does conclude section 4.2. Have a great one.